Have you ever really stopped to think about heat? It can cook our food, but it can also totally ruin our ice cream. So today, we're going to pull back the curtain on how heat actually moves from one place to another. And it all starts with a really simple question you've definitely asked yourself before.
Okay, so here's the puzzle. Just picture this. You're walking around your house, barefoot. You step off a nice soft carpet and onto a marble or tile floor. Whoa, that marble feels so much colder, right? But what if I told you they are both at the exact same temperature? I mean, to the degree. How is that even possible? Well, the answer to that little mystery is all about understanding how heat gets around.
So what you're feeling there is a classic physics principle in action. The secret isn't about how much heat the floor has, it's about how fast it can pull heat away from your feet. That's the key. This whole process is called conduction, and it's going to be our first stop on our journey into heat transfer.
And here's the cool part. It turns out that pretty much all the heat moving around in the entire universe does so in just one of three ways: conduction, convection, or radiation. So let's break down each one, and you'll start seeing them everywhere in your daily life. I promise.
All right, first up, conduction. The easiest way to think about conduction is heat transfer through direct touch. It's like a microscopic game of hot potato where energy gets passed from one particle to the next.
Now, here's the absolutely crucial part to remember about conduction. The material itself doesn't actually go anywhere. It's only the energy that's traveling. The atoms in a solid, for example, they just stay put. They just vibrate more and more energetically and pass that vibration, that energy, right down the line. And this image shows it perfectly. When you heat one end of this metal rod, the particles there get a jolt of energy and start vibrating like crazy. They then bump into their neighbors, who start vibrating and bump into their neighbors, and so on and so on. It's literally a domino effect of energy, passed right along the rod. But of course, not all materials are created equal when it comes to this. Metals are amazing conductors, partly because their atoms are packed so tightly, but also because they have these free-flowing electrons that can carry heat energy super fast. On the flip side, things like wood, plastic, and especially gases are really bad at this. We call them insulators. And that brings us back to our floor. The marble is a good conductor, so it yanks the heat from your foot really fast, making it feel cold. The carpet? It's a terrible conductor, an insulator, so it transfers heat much, much more slowly. Okay, time for a quick challenge. Let's think about a simple styrofoam cooler. We all know it works, right? But based on what we've just covered about conduction and insulators, can you figure out the science behind why it's so good at its job?
Did you get it? The secret ingredient is air. Styrofoam isn't a solid block of plastic. It's actually filled with millions of tiny, trapped pockets of air. And as we just said, gases are terrible conductors. So all that trapped air acts like a barrier, massively slowing down the transfer of heat from the hot outside to your cold drinks inside. It's the exact same principle birds use when they fluff up their feathers in the winter. They're trapping air to insulate themselves. Pretty clever.
Okay, on to our second method, convection. Now, if conduction was all about particles passing energy while staying put, convection is the complete opposite. It's all about movement. This is heat transfer that literally goes with the flow.
The big difference here is the physical movement of the stuff itself. The actual particles travel from one place to another, carrying their heat energy along with them for the ride. And that's exactly why convection only happens in fluids, liquids and gases, because their particles are free to actually move around.
The best example is just a simple pot of water on the stove. The flame heats the water right at the bottom. As that water gets hotter, it does something interesting. It expands. And when it expands, it becomes less dense than the cooler water sitting on top of it. So what happens to something that's less dense inside a fluid? That's right, it rises. So as that hot water rises, the cooler, denser water from the top has to go somewhere. So it sinks down to the bottom to take its place. And what happens when it gets to the bottom? Well, it gets heated, becomes less dense, and rises. This creates this amazing continuous circular flow called a convection current. It's basically a heat-powered conveyor belt that stirs the water and distributes heat everywhere.
So let's use that idea. Have you ever wondered why air conditioners are always installed way up high on the wall, near the ceiling? It's not for looks, it's pure physics. It's designed to create a giant convection current in your room. The AC unit chills the air around it, making that air denser. That heavy, cool air naturally sinks to the floor, pushing the warmer, lighter air upwards. And where does that warm air go? Right back towards the AC unit to be cooled.
It's a brilliant, self-sustaining cycle that cools the whole room efficiently.
All right, it's time for our third and final method of heat transfer. And this one is, well, it's a bit different. Let's talk about radiation. This one is super unique because it doesn't need any particles at all. No medium, no touching, nothing. It's just pure energy taking an invisible journey through space.
Radiation moves heat as electromagnetic waves, specifically what we call infrared waves. Just think about this for a second. This is how the sun's unbelievable heat travels 150 million kilometers across the total vacuum of space to reach us here on Earth. If it weren't for radiation, our planet would just be a frozen, lifeless rock.
Now, what's really fascinating about radiation is that we can actually control how fast it happens. There are three main factors, or dials, you could say, that we can tune. How hot the object is, its total surface area, and this one's huge for everyday applications, the color and texture of its surface.
And when it comes to color and texture, there's one golden rule you have to remember. Dull, black surfaces are fantastic at both absorbing and giving off heat radiation. Think about how hot black asphalt gets on a sunny day. On the other hand, shiny, light-colored surfaces are terrible at absorbing and emitting heat. Instead, they're great at reflecting it. That's why a giant fuel storage tank is painted a brilliant white to reflect the sun's heat away. And it's why a fancy teapot might be made of shiny silver, to be a poor emitter, keeping the tea inside hotter for longer.
Okay, time for our final brain teaser. Take a look at the back of a refrigerator. You'll almost always see these big, metal, grid-like fins, and they're usually painted a dull black color. Why? What's the point of designing them that way? Think about what a fridge's main job is, and the rules of radiation we just talked about.
So the answer to the fridge question? Well, a refrigerator's job is to pump heat out from the inside. The fins are made really large to maximize their surface area, and they're painted dull black because that makes them a super efficient radiator, dumping all that unwanted heat out into the room. So now that we've seen how to get rid of heat efficiently, let's look at an absolute marvel of engineering that's designed to do the exact opposite, the vacuum flask.
Let's break down how this thing works, because it's pretty brilliant. It fights all three types of heat transfer at once. First, it has a vacuum, a layer of nothing between its inner and outer walls. No particles means you've just stopped conduction and convection cold, dead in their tracks. Next, the stopper on top is made of an insulating material to reduce conduction through the lid, and you screw it on tight to stop any convection from happening there. And the final touch? The inside walls are often coated with a shiny silver layer. Just like that shiny teapot, this surface is a terrible emitter and a great reflector, so it reflects heat right back to where it came from. It's an elegant solution that attacks the problem from every angle.